Welcome my friends to my YouTube channel. Now yesterday I have finished the Maxwell's relation chapter. Now in today's video I shall going to discuss the fifth chapter of thermodynamics, that is the phase transition. Okay. So today we shall discuss about phase transition. Okay. Phase transition. So here at first we have to know what is phase. Okay, the first question arises, what is phase? Okay, now a phase is nothing but a form of matter that is chemically or physically homogeneous. Okay, so basically it is nothing but a form of matter. So it's a form of matter that is chemically and physically homogeneous, or you can say uniform, or uniform. Okay, so it is a form of matter that is physically and chemically homogeneous or uniform. Okay, just consider an example. Say ice, water and vapor. Just take this example, ice, water and vapor. Here it is a three-phase system. Okay, so there are three phases. One form is ice, that is solid, another is water, that is liquid, and another is vapor, that is gas. So solid, liquid and gas. So basically it is a three-phase system. Okay, it is a three-phase system, and each phase is separated from other phase by distinguishable boundary, obviously. So there is a distinguishable boundary, there is a distinguishable boundary between any two phases. Okay, so basically a form of matter that is physically or chemically uniform. Here we took the example of ice, water, vapor, that is solid, liquid and gas. It constituted, there are three phases in this system and each is separated by a distinguishable boundary. So you can also give a definition, that is a homogeneous part of a heterogeneous system that is separated from other parts by distinguishable boundary is called a phase. You can also define it. Okay, so you can also define it in terms of this, a homogeneous part of a heterogeneous system that is separated from all other parts by distinguishable boundary. Okay, so another definition you can write, that is the homogeneous part of a heterogeneous system, of a heterogeneous system that is separated from other parts by a distinguishable boundary. Huh? Homogeneous part of a heterogeneous system that is separated from all other parts by a distinguishable boundary is called phase. Or you can also write down the previous definition, that is it is a form of matter which is chemically or physically homogeneous. Okay, each form is homogeneous to itself. So this is what is phase. Now the second question that arises, what is phase transition? The second question that arises, what is phase transition? Okay, what is phase transition? Now Phase transition is nothing but the transition from one state to another. The transition from one phase to another phase of a thermodynamic system. Okay, so transition from one phase to another. So basically it represents the transition from one phase to another. Just take a suitable example. I just we draw the pressure temperature diagram, that is we consider the triple point example. This is a familiar example and we will also learn it later in details. So what happens in pressure temperature diagram, if we draw, then there are three curves, you all know it. Say this is point O where the three phases coexist. So this is solid, this is liquid, and this is vapor. Just give it a name A, B and C. So O is the point where for a particular pressure and temperature all the three phases exist simultaneously. Okay, and this line OA represents the equilibrium line between the solid and liquid phase. The line OB represents the equilibrium line between liquid and vapor phase. Similarly, the line OC represents the equilibrium line between solid and vapor. So in general, we can say O is the point where all the three phases coexist. OA represents the line between solid and liquid, OB liquid and vapor, and OC solid and vapor. Okay, now we all know that this is the critical point. Okay, this is the critical point, and below critical temperature a gas always be converted to liquid, but beyond the critical temperature we cannot convert a gas to liquid by the mere application of pressure. Okay, so for T less than Tc, gas cannot be converted to vapor, cannot be converted to for T less than Tc the gas can be converted to vapor. Okay, but for T greater than Tc the conversion is not possible, because critical point is the point beyond which a vapor cannot be, a gas cannot be converted into liquid by mere application of pressure. So this is the example, we took the example of critical point, triple point, where for a particular pressure and temperature all the three phases exist simultaneously. Okay, this represents the equilibrium line between solid and liquid, and this is liquid and vapor, and this is solid and vapor. Actually this is the sublimation curve, this is the vaporization curve. Okay, and this is the fusion curve. Okay, more commonly OA is called fusion curve, OA is called fusion curve, OB is called vaporization curve, vaporization curve, and OC represents the sublimation curve, sublimation curve. Okay, so this is the definition of phase transition, that is transition from one phase to another phase, and as a result we take the example of triple point, and we also learn it in later. So I just give an example. Okay, now the third thing that arises, what are the different types of phase transition. Okay, now you all know that there are two types of phase transition. Now today I shall discuss about the first order phase transition. Okay, today I shall discuss about the first order phase transition, and what is it and what are the properties of first order phase transition. Okay, now first thing that you have to remember, that in first order phase transition entropy and volume changes. Okay, this is the thing, entropy and volume changes. This is the first feature, that in a first order phase transition entropy and volume changes. Okay, now this second feature is that whenever there is a change from one phase to another, there is a transfer of energy, and this is governed by Clausius-Clapeyron equation or fast latent heat equation. So since the phase transition involves transfer of energy, okay, transfer of energy which is governed by fast latent heat equation. So first order phase transition is governed by fast latent heat equation, or you can say Clausius-Clapeyron equation. Okay, Clausius-Clapeyron equation. So this is the second feature, that whenever there is a phase transition occurs, there will be a transfer of energy, and for first order phase transition it is governed by fast latent heat equation or Clausius-Clapeyron equation. Okay, now Gibbs potential that changes continuously. Okay, there is a continuous change of Gibbs potential. Okay, continuous change of Gibbs potential. How? So in order to explain this, that there is a continuous change of Gibbs potential, just I have to draw a picture, that is, just draw the Gibbs potential versus the temperature curve. You take Gibbs potential here, and this is temperature, and this is the transition line. This is say phase 1 and this is say phase 2. So there is a continuous change. That means if you plot a curve, it looks like this. That means at the this is called transition point, the changes you see continuous. Okay, so this is the transition point. Okay, there is a continuous transformation or continuous change of G. So you must have to remember that in case of a first order phase transition, if you draw a curve between G and T, and this represents the two phases, and there is a, you see, this is the transition point where the two phases meet, there is a continuous change, no discontinuity is observed. So continuous change of G, continuous change of Gibbs potential. Okay, continuous change of Gibbs potential. Okay, so now the first order derivative of Gibbs potential changes discontinuously. What do you mean by that? Here we see that the change of Gibbs potential is continuous, but its first order derivatives changes discontinuously. How? So you can write G, this is U plus PV minus TS. Now what will be dG? We all know that is du plus PdV plus VdP minus TdS minus SdT, and du plus PdV means dq means TdS. So this is VdP minus SdT. Okay, now if you add an extra term, that is chemical potential term, you can write it, which is associated with the number of particles dN. Just add it, or if you don't add it, no matter, but later we have to understand what is this. But till now, if you add this, it's okay, and if you don't add this, no problem. So these are the quantities, so from which we can write V is what? Del G del P at Tn, or you can say what will be my S, or you can say del G del T minus this is at Pn. Okay, or what will be my mu, or you can say del G del N at P say T. So thus you see that first order derivatives are not continuous. Okay, they are discontinuous. So if you plot a curve, so what will be the nature of the curve? Okay, so if you plot it in curve, say you plot this curve, that is you take temperature and you take say del G del P temperature constant, then there is a discontinuity, that is say this and this. Okay, so there is a discontinuity at the transition points. Okay, because there is a discontinuity at the transition points. Or if you plot another curve, say this is t and this you take say del g del t pressure constant, then it will also be discontinuous. Okay, it will also be discontinuous. There you see that these curves are not continuous. A discontinuity is observed at the transition point. Okay, so in first order phase transition gives potential changes continuously, but first order derivatives changes discontinuously. So you can conclude that first order derivatives of G are discontinuous. Okay, now what are the familiar examples of first order phase transition? Now we all know that familiar examples. What are the familiar examples? That is, you can say conversion of solid to liquid, conversion of solid to liquid, or you can take conversion of liquid to vapor, or you can take vapor to solid. These are all the examples of first order phase transitions. Okay, so if you take examples, then all are the examples of first order phase transitions. Okay, so solid, conversion of solid into liquid, liquid to vapor, and vapor to solid, these are the examples of first order phase transition. Okay, now I already told that this phase transition is governed by Clausius-Clapeyron equation. Now let us check whether Clausius-Clapeyron equation agrees with the expression that we observed earlier. That means by using previously we derived the Clausius-Clapeyron equation by Maxwell's relation. So now let us try to find out the Clausius-Clapeyron equation in terms of Gibbs potential. Now we will study it later that the condition of equilibrium between the two phases is that their Gibbs potential must be equal. This is the equilibrium condition between the two phases, which we will study later. Okay, this is the equilibrium condition of two phases that we will study later. So let us check whether starting from this condition we arrive at Clausius-Clapeyron equation or not. So 1 and 2 represents the initial and final phase. So you can write dg1 this equals to dg2. Now what will be my g? My g will be, since I give here small letters, I also put all small letters. So what will be my g? du plus pdv plus vdp minus tds minus sdt. So du plus pdv tds cancel, so what we get? vdp minus sdt. Now we have to substitute this value in these relations. Okay, vdp minus sdt. Okay, so what will be my dg1? That is my v1 dp minus s1 dt. And what is this? v2 dp minus s2 dt. Okay, so if we take dp common, then what we get? v2 minus v1, and if we take it common, dt common, then we get s2 minus s1. Okay, so what will be my dp dt? That is s2 minus s1 by v2 minus v1. Okay, so we multiply both sides by t. So what will be my ts2? My ts2 will be q2, and what will be ts1? q1, and this is simply t into v2 into v1. Okay, and what is q2 minus q1? L. So L upon T, V2 minus V1. So L represents the latent heat per mole, and V1 and V2 are the specific volumes in initial and final phase. If we consider 1 mole or unit mass, whatever you can say, this volume is known as specific volume. Whenever we consider 1 mole or say 1 gram or unit mass, this term becomes specific volume, and this is q2 minus q1 means a latent heat per mole. Okay, so we arrived at the Clausius-Clapeyron equation. Okay, so L is what? L is latent heat per mole. So thus we also arrive at Clausius-Clapeyron equation from the concept of equilibrium condition between the two phases. Okay, and this equation is exactly similar as we obtained in earlier by using Maxwell's relation. Okay, so first order phase transition is governed by Clausius-Clapeyron equation. Okay, now in my next lecture I shall discuss about the second order phase transition. Okay, so dear guys, if you don't subscribe my channel, then kindly subscribe it to get latest videos on physics. Okay, thank you.